So I'm going to start recording now, and yeah, we can get started, and I can welcome everybody who's here. Sorry, I'm just seeing someone else here. Hand raised. Yeah, so I can welcome you all to the Better Building Speaker Series. I'm Claire Morley. I'm an Energy Efficiency Officer with the Ecology Action Center. Before we do anything, I'm just going to give a quick land acknowledgement and acknowledge that we are hosting this webinar from Mi'kmaq, or also called Nova Scotia, and it's unceded Mi'kmaq territory, and most of us are visitors on this particular territory, and I just ask that everyone consider this as, you know, we walk on this land and we continue with tonight's discussion. Yeah, and so the Ecology Action Center is a member-based environmental charity in Nova Scotia, and we take leadership on critical issues from biodiversity to climate change or environmental justice. And the Better Building Speaker Series is something that we run in partnership with Efficiency Nova Scotia. And thank you to Efficiency Nova Scotia for their financial support for hosting these webinars. And it's really just an opportunity to talk about different ideas and different projects going on in the efficiency sector. So without further ado, I'm going to introduce Nick Rudnicki, who is the CEO of RSI Projects and the technical director of the Recover Initiative. He's going to be giving the presentation tonight on Panelized Retrofits and the work that he does with the Recover Initiative. Really happy to have him. If you have any questions, you can use the Q&A form at the bottom of your screen in the toolbar. You can see it just says Q&A, and you can use that to post any questions you might have during the presentation, and we'll go through them. We'll have a little period at the end of the presentation where we can pick Nick's brain and get some answers out of him. So Nick, I'll let you take it away.
Thanks, Claire. Though I will warn everybody, 6 p.m. on a Wednesday, there's not much of my brain left to pick, so calibrate your expectations proportionally low. So just to flesh out the introduction a bit further, as Claire mentioned, I'm Nick Rudnicki, CEO of RSI Projects, a residential building company that's been around since 2011. I should probably know that better, but we've been around for about a decade plus. And I've always had my focus on high performance, high efficiency building renovation. And I've come to appreciate that we're not doing enough from a green building perspective, not making enough of an impact on the climate emergency, and we need to figure out a better way. In fact, I mean, the presentation will explain it a bit further, but it was about 3 years ago that I kind of had this existentialist crisis of like, I think I need to be doing a whole lot more, and I don't know how to do it. And my colleague, not colleague, she was a designer that I worked with, Lori Rand, suggested that I look into, this is all covered in the presentation. What am I doing here? Rambling away. So without further ado, let's get to the pretty graphics. Let me just get that going. That is not the right button for me to be pressing. There we go. We want to be sharing that. So everybody just somebody give me a thumbs up that you can see that. Oops, no, you can't see it yet. Should be able to see it now. I can't hear anyone.
I think it's just loading. It says you've started to share your screen, but I can't see anything just yet.
My screen sharing is paused. Resume share. Resume share. Well, that's dumb. Me and Claire just did this like 20 minutes ago to avoid exactly this kind of silly delay. So apologies. Let me try and get to the bottom of this. Now you can
Beautiful.
see a giant Recover logo, I hope.
I think we can all see it.
Great. So charging right into it. I'm here not with RSI, although that's part of my background. I'm here with the Recover Initiative, something that was formed almost 3 years ago with Emma Norton, Lori Rand, and myself as our sort of collective response for trying to help accelerate the buildings part of the climate crisis. So speaking of climate crisis, that's what drove us all here. Hopefully drove you guys as well. And I borrowed this slide from a presentation that I like, some Spanish, doesn't matter. I stole this. I'm not this clever to start the climate emergency is real. It's happening right now. You guys have seen the weather reports and you've seen what's happened in Europe, massive droughts in China. It's actively happening. The time to act is about 50 years ago, but tomorrow is just as good, or the best we can do, I guess. For those of you that aren't mired in the climate conversation and might not be familiar with some of the language, it really all comes down to carbon. Not specifically the atom carbon, but the word carbon, and specifically CO2e. Which might be new to you, but to be clear, it's carbon dioxide equivalence, meaning that we're all familiar that carbon dioxide has a greenhouse gas potential. You put a lot of carbon dioxide in the air, atmosphere retains heat, we start getting hotter. But there's all sorts of other gases and compounds that have greenhouse gas potential. So, for example, 1 unit of methane is the equivalent of 25 units of carbon dioxide. 1 unit of gasoline is equivalent to 2.35 units of carbon dioxide. So the idea behind using CO2e is that way, no matter what the pollutant, no matter what the emission is, we have one fundamental unit of like, okay, this is how we're going to universally talk about the climate impact of this thing. So that gives us a climate change currency that we can use across the board. We can use them to fairly measure and compare the impacts of this choice versus that choice. Okay, so a little bit of definition out of the way. Which brings me to, I started rambling in my own intro about the little existentialist crisis that I had 3 years ago. I started learning about this carbon cost of building materials. That building materials themselves have a carbon footprint before you even turned on the building. That kilogram of concrete that shows up not only took an incredible amount of CO2e or made a lot of emissions being made, it also made a lot of emissions being shipped, and it makes a lot of emissions as it's being installed because of all the fuel that needs to go into all the vehicles that bring all the people, the pump truck that shows up, all these things. If you do a carbon audit of the average construction site, it is astonishing what goes on. So the idea of the carbon cost or the embodied carbon of building materials is exactly that. The summary, the bottom line of everything that's involved in making that material and getting it to the building site. So, for example, something like, let's pretend this is drywall board. You need to mine the gypsum. You then need to transport the gypsum to the processing plant. The processing plant needs to invest a whole bunch of energy in milling that gypsum and squeezing it between 2 layers of paper to make a drywall sheet. Then those heavy drywall sheets go onto a transport truck, which goes to a distribution center, goes onto another transport truck to get to the job site. By the time that gypsum's arrived, we've released really embarrassing amounts of CO2e to get it there. That means that sheet of drywall has an embodied carbon. It literally embodies a carbon footprint. That's depressing. So it's not all bad news, because if you were to take advantage of the miracle of plants, particularly trees, you may be familiar with how many trees we use in contemporary construction. Because here's a little fact that 5 years ago blew my mind. The vast majority of the weight of a tree is literally made out of carbon dioxide, because the tree or plant, whatever the case may be, pulls carbon dioxide from the atmosphere and burps out oxygen. That's elementary school, maybe junior high level biology. But that carbon that gets pulled out actually stays and becomes the vast majority of the weight of the tree, meaning that the plant or tree is literally made out of CO2 that was pulled from the atmosphere. So every kilogram of tree represents actually a couple of kilograms of CO2 you pulled from the atmosphere. Great. Now, that means that when we start off with the tree growing in the ground, it has absorbed a lot of carbon dioxide. It is locked in that carbon and pulled that CO2 out of the atmosphere. And then as you harvest, transport again, and distribute it, you're going to be releasing a little bit. But if you've done it right and you've done it responsibly, you can actually end up with a negative carbon value or negative CO2e value for the product. So meaning that the fairly dull chart of numbers, but check it out. In green are the carbon negative materials, meaning that 100 kilograms of lumber, so a small pallet of wood, actually represents 150 kilograms of CO2e that was pulled out of the atmosphere and is essentially stored. We're not allowed to say sequestered. Is stored in that lumber, unless, which is in diametric opposition to say like 100 kilograms of concrete, in which point that 100 kilograms of concrete represents 37 kilograms of CO2e that was released. And then glass is much worse, and fiberglass is the worst of all. And then cellulose insulation, more on that later, also has a really positive carbon footprint. So there's a carbon penalty to the building material choices. And plant-sourced building materials can be potential carbon storage. Keep that in mind. So the buildings problem, the climate emergency part, we're clear on that. That's why we're all here. But what role do the buildings play in it? And when you say the buildings problem, most people would imagine, oh, okay, so new buildings need to be built more efficiently and built with more carbon responsible materials. True. Because nearly 30 million gigajoules of energy was used to heat Nova Scotian homes in 2016. I should get more updated stats. I know. 17% of all of Nova Scotia's energy demand. So that's like almost a full fifth. So a meaningful slice of the energy pie is being used to heat existing homes. You keep in mind the existing part. And because of how irresponsibly we heat with, kerosene, 42% of Nova Scotia's emissions come from our buildings. So not only do we use a meaningful amount of energy, but we're using a tremendous amount of responsible for a tremendous amount of these emissions. Again, these are 2016 numbers, they're not exactly accurate, and I haven't compiled the national numbers. But this gives you a sense of what motivated us to move in this direction. So here's kind of the crux of it. Because even if every single building was built net zero out of nothing but like hemp and cellulose and all these super responsible materials and done with like hydrogen fueled trucks and everything was green and no more emissions from new buildings or their production, that doesn't really matter. Because a perfectly efficient new buildings cannot have an impact on the existing ones that we're going to keep using, because we're not going to demolish every single building in the province and then all of a sudden have replace it with so we've got a huge debt embodied in these old buildings. So we have to retrofit the existing buildings because they're not going anywhere. I mean, we could go on a campaign of demolishing them and rebuilding, but then we're back to the whole sort of carbon footprint of construction, and never mind the embodied carbon of demolition itself. So we're here to retrofit. And when I took this problem, as I mentioned before, I had this existentialist crisis, and I took it to my favorite designer, Lori Rand, and she introduced me to this Dutch idea of Energiesprong. And I'm not pronouncing it correctly, but the idea is simple, and we've rebranded it as Recover, which should be apparent in a second. You start by measuring the existing building. Nowadays, you can do it with tremendously cool LiDAR, more on that later. You take these precise measurements, you give them to the factory or assembly plant, they make perfectly sized panels that will fit onto the building. You take those panels you ship them to the site, you crane them onto the building. And these panels in the Energiesprong model contain everything that you need. There's the actual box of the panel itself. It's full of insulation. It has air tightness built in. For those of you that don't know, air tightness on a retrofit is probably the most important part. The windows are already in, the doors are already in, the siding is on. and if applicable has like sometimes wiring and ducting run through it as well, so that you just take these panels, click them onto the building, get the seams buttoned up on site, and ta-da, a new high performance envelope around your existing building, because we've recovered the building, and we've also helping it recover from the climate crisis. It's a very clever name. So that all starts with the LiDAR scanning. The little Faro focus box you see on the left side of your screen is a LiDAR scanner. It rotates around, takes billions of data points from the building, and gives you what you see on the right. That's not a blurry photo. That is literally several million or billion, I didn't stop to count them all. Those are all data points that are also color-coded to represent what that surface color actually was. And that gives you this nice raw data of exactly what that building is shaped like, which allows you to take it into a CAD environment and start planning and mapping out panels that will fit onto this building without needing to be there, without needing to build it on site, without needing to custom build it to the building. You can just take it to the factory floor, have it built. As you can see, have it built on the factory floor where everybody's out of the weather, working at safe heights, working under controlled, safe environments. Your quality control is much, much easier because all of a sudden you're not doing it in the like blazing hot sun of August or the frigid, blustery conditions of February. Climate controlled, ready to go, super easy to make a much, much better panel. Then you just crane it into place. So instead of hanging out on scaffolding for days and weeks and months and years, just bring in a panel, click it on, fraction of the time. The idea would also be to maximize the use of carbon storing materials. So coming back to that idea, because if we can do this right, that means that each project that we retrofit, we basically have created a carbon credit, so to speak, with every project, or a carbon store. We still haven't settled on the most precise language about it, but you get the idea. So let's quickly walk through a case study we did 2 years ago. 6300 Lawrence Street, just down the street from my house. Fun coincidence. This building used 149 kilowatt hours per meter squared, which is only slightly better than the national average. So we thought it was a really good starting point to see whether or not it made sense. The aforementioned LiDAR scan was done. This was extrapolated into a very detailed CAD drawing, which we could work with in 3 dimensions to do things like figure out the panel layout. How exactly would these panels fit onto the building and interact with themselves, run interferences with would it collide with this window, and how to deal with this, that, and the other. So map out the panels. And then we drilled into the details of okay, well, how would we actually make it attached to the foundation? How do we get the air barrier nice and tight here and there? The structural engineer needed to confirm, okay, is it going to be able to take all this weight? How are we going to attach it to the building? Work through all those details to demonstrate that it was doable. Now, I mentioned the air barrier, which meant that this new wrap around the house, these panels around this building, would have created an airtight shell, or a much tighter shell. Perfectly airtight is extremely difficult, but much more airtight, which means that the building would sort of end up suffocating a little bit. Hence the need for an ERV and energy recovery ventilation. More often than not, people use HRV, heat recovery ventilation, splitting hairs, fresh air intake with heat exchange. But also, if you're super insulating the building and making it airtight, that means it's going to hold on to a lot more heat, which means the giant boiler that's in there is no longer needed. You can electrify, go with mini splits and a backup electric boiler. And then when we put it all together architecturally, it's also an opportunity to upgrade. Gone is the brick and the sad old windows, and you've got fresh metal cladding because metal has an extremely long lifespan. So we opted for that. And look at what you can do. Okay, but what kind of performance results did we get? On paper, we were able to demonstrate that with that level of insulation, with that target of airtightness, and with the window improvements, and with the solar panels being put on top, basically every option we looked at got us to net zero. So we can get to net zero. That's fantastic. We were able to reduce the energy demand by 75%, down from 95,000 kilowatt hours to only 24,000 kilowatt hours. And most of that was stuff like plug load and appliances. Only a small portion of it ended up being heat. Now, Lori Rand ended up doing an extensive analysis of the CO2e storage capacity of this project. And based on existing databases of building material, embodied carbon loads, et cetera, we were able to show, and I know it's kind of teensy on your screen, but that is 76,000 kilograms of CO2e being able to be stored in the building material. Never mind the emissions avoided by the new, much more efficient heating system. This is just the building materials. We also knew that we needed to do an extensive financial analysis to, make the business case, or start to make the business case. It's like, okay, so TCBO steps in, total cost of building ownership. And this took into account, like everything, the cost of doing the actual original install, the expected carbon tax escalations, expected energy cost escalations. And the modeler was actually fairly conservative. So these are likely low, but we can't see into the future. So we'd rather just model the conservative numbers. It took into account like likely insurance costs, the maintenance burden of the various appliances and systems that we're installing. After 25 years, some of those windows might need to be replaced. The roof membrane needs to be replaced after another 15 years, what have you. All of that taken into account and extrapolated, which meant that after 60 years, which is a long ROI, I understand, but after 60 years, which is, essentially the useful lifespan of a rejuvenated building like this, it has cost you $1.5 million less to own and operate this building. That's pretty staggering. Okay, so great, that sounds revolutionary and amazing, but we can kind of get there with conventional retrofits, right? Well, what compels us to be chasing after this panelized, prefabricated offsite system are a few of the following. Most deep energy retrofits, and anybody who's been at the EAC for, how long ago was it, 5 years or more, will attest to the fact that retrofitting that building, and they did a tremendous job of it. They took it from very low level to very high level. They did great, but the EAC needed to be empty for almost a year. So if we're doing this to, tens, hundreds, thousands, tens of thousands of buildings at a time, that's a lot of displacement. And we can't do that. So the recover system, people can stay in the building. They keep living and the panels are just clicked on around them. Maybe, yeah, they need to walk kind of around a construction site to get home, but they get to stay home because you don't have to do any of this. A conventional retrofit is incredibly time consuming, in part because of this, where the recover approach means that the bulk of the actual work happens off-site. You can just come to site and click it on and walk away. I mean, grossly oversimplifying, it is more complex than that, but things happen in a fraction of the time. The Energiesprong projects that have taken place in Europe, particularly in the Netherlands, where it started and where it's sort of most mature, they started by having one retrofit taking about a week and a half on site. And the most efficient iterations of it nowadays are a day and a half. So the crew shows up at 8 a.m. and by, say, 6 p.m. that same day, you've got a net zero house. Holy cow. You can't do that with conventional approaches. Conventional approaches are also very complicated because conventional approaches basically have to look at the building and not know what's inside the building and have to look at, okay, so we have to demolish all the siding or maybe gut it on the inside, and we have to evaluate whether or not this will work or that'll work. And it's a complex beast. So that also feeds the time-consuming and disruptive part. They are going to be expensive because there's no economy of scale. Like, it doesn't matter how many conventional retrofits you do, you always have to be up on a scaffold and replace that old window and deal with whatever structural rot issues are in the middle of winter or the blazing hot sun, it doesn't matter. And then you have to crane that new window in and put it in and caulk it into place. It's just super difficult to work on an existing building as it stands. And finally, they're all custom because every building will throw up problems that will complicate how you have to execute it. Where the recover concept and the Energiesprong concept is to basically get it as close to an IKEA prefab idea as humanly possible. Yes, I understand, we exquisitely understand that every building is unique, but if we can streamline that process, when we streamline that process of building image capture, LiDAR image capture, and be able to feed it into the algorithm that can then spit out, cool, these are the panels you need and this is how you install them. You know, it goes from being a bafflingly long research and development and design process to simply something that it becomes a plug and play problem. We're far from it yet, but that's where we need to get to. So, you know, if we know there is a better way to do it, there has to be a better way to do it, because oh my God, do we have a lot of buildings to try and rescue and recover and try and get out of the tailspin of this climate emergency, because I don't know about you guys, but I find it kind of alarming. So that's the, oops, let me stop sharing. So that's the sort of the very long elevator pitch for recover. Hopefully that's shed some light and maybe inspired some questions. Is there nothing going on in the Q&A just yet, so I will hand it back over to Claire, but that's it for the sort of formal part of the presentation. I'm here for a little while yet, so I'm happy to field any and all questions, because I know there's probably a few of them, on account of this being so non-standard.
Yeah, thanks, Nick. If anyone has questions, like Nick said, feel free to pop them in the chat. That was really great. That was really comprehensive. I feel like I saw the whole life cycle of construction happening before my eyes. And very engaging as well, if you don't mind me saying so. But yeah, I think we have a question from Brenda in the Q&A section. And so yeah. I think the question is about the building on St. Lawrence, yeah. On Lawrence Street, sorry. Lawrence Street.
Here, so I'll just tackle some of Brenda's question. I saw a hand go up, but it seems to have gone down. We're on Lawrence Street. What happens to the windows? Are they double windows or what? Asks Brenda. So it is 6300 Lawrence Street, which is 2/3 of the way up the street if you're coming from Windsor, and 1/3 of the way down the street if you're coming from Oxford. What happens to the windows? The panels that are flown in and installed end up basically having windows exactly overlapping the existing windows, which means that, yes, so there's a kind of double window situation for a minute or two, but once the building is all covered and the new envelope is weather tight, crews go into the building, remove those existing windows, exposing the newly retrofit ones, and then build out a window buck to connect the interior of the space with the now much deeper out, further out window. Which on projects that have used similar approaches, most of the occupants are like, wow, look at my great new deep window boxes. I'm going to hang out here and read a book. Not really paying much attention to the energy performance because they just love their window box. So that's pretty exciting. Brenda also asked, is anyone else doing this now? And how is this funded? So it's a two-parter. Is anyone else doing this now? Exactly the way we want to do it with the carbon conscious material choices? No. But in North America, in Canada, in North America, there's a number of initiatives in California to get this kind of work off the ground. I understand there's a number of pilots there. NYSERDA in New York has done some studies and they actually executed a few projects. I'm vaguer on those details because I'm more knowledgeable of what's going on in Canada. In Canada, going west to east, we've got Peter Amarongan in Edmonton, Alberta. There's a 50-unit housing co-op called Sundance, which is currently in the midst of a retrofit along these lines, where panels are being brought on and then being filled with cellulose on site. So they're doing a semi-panelized thing, like panels are involved, but they're still doing a great deal of work on site. There's also Ottawa Community Housing, who's working with NRCan and CanMet Energy. They collaborated on some research work to figure out a panel system that should work for a number of their buildings. And I believe they've finished their first one with very clear intentions to do tens more of them. Ottawa Community Housing, to the funding question, is paying for it out of their own coffers because they did the financial analysis and it didn't make sense for them not to do it. I believe there's some support funding from, I want to say CMHC. I'm vague on the funding details on that one. I know that the project in Edmonton is being funded through, in part by the co-op's budget itself, because it represents a substantial maintenance upgrade. So their operations budget is paying for a good portion of it, and NRCan kicked in some support funding, which they actually haven't used a ton of last I checked in. So they're running pretty lean. Though with building material spikes, I'm pretty sure that has changed. So that's Brenda's two of Brenda's questions. Callan, I hope I'm pronouncing that right, wonders how long to manufacture the panels. Well, the panel manufacturer, that's a question for the factory. Because if it's just one person in a garden shed, it's going to take a long time. But a well enough organized factory floor, I guess probably the best example would be prefabricated construction panels aren't a brilliantly brand new idea. It's been happening for the last couple decades, more or less. There's a lot of new construction going on in the United States and some here in Canada that's happening with these prefabricated panels. And probably the best example of that is a firm called Benson Wood, and started by Ted Benson, who actually took my call a year ago. It was great. Their factory is so dialed in and so automated and so precisely honed that from pile of lumber to a panel with window ready to be turned into a house takes like 45 minutes. It's really shockingly efficient. But that is a substantial investment in quite a lot of robotics, quite a lot of automation. So how long does it take to manufacture the panels? Forever, or just a few minutes and everything in between. So it's not straightforward, but I can tell you from our experience, because we've panelized a couple of projects with RSI projects, and we were finding that with a well-oiled team of 4 people working in a relatively well-equipped shop, they were able to put out 1 panel a day. And even that was sort of like, we were still learning things, we were still getting more efficient, there's still things we could have done to make it quicker. But you know, a panel a day for a reasonable outfit is not at all out of the question. Brenda then also chimed in with the question, how thick did the walls end up being? So for the 6300 project, the 6300 Lawrence Street, the case study that we looked at, I believe the depth of the wall was, or the panels was 8 inches. I think it was 8 inches on that one. So it did mean that like the existing wall and the new wall together, quite a deep wall, but the panels themselves weren't as thick as I thought they would need to be, because you ended up being able to take advantage of the fact that your surface area to volume ratio was favorable. So not terribly thick on this one, and they don't need to be terribly thick because we only need to add insulation to what's already there. So in buildings that are already kind of semi-adequately insulated, you know, the panels don't have to be very thick, but they do have to be airtight because that's where most buildings fall down. Rabail, again, hope I'm pronouncing that right, apologies if I'm butchering it, asks, thanks, or mentions thanks, it's totally inspiring. What's the most complex challenge you have faced up until now while retrofitting existing buildings, and how did you resolve it? Full disclosure, we haven't actually retrofit a building. We're still very much in the market development, advocacy, research phase. But I can speak on behalf of the 2 projects that we're quite friendly and communicative with, which would be Sundance in Edmonton and Ottawa Community Housing in Ottawa. From them, I know that in Edmonton, the most unexpected challenge was the electrification component. The Edmonton utility is like, cool, you want a whole bunch of electricity, that's great, but we're going to have to spend a lot of time and energy and money upgrading the transformer that services your neighborhood, because you guys are now suddenly going to need a lot more electricity than the current transformer can provide. And that meant that there was a lot of underground trenching, because it's Edmonton, so the power lines are underground, a lot of underground trenching to every unit and upgrading people's what are they called? Not control panels, breaker panels. I do this for a living, I swear to God. So the upgrading the transformer and all that electrical upgrade created tremendous delays and considerably more expense than they had budgeted for. So I know that was one of the big sort of complicating factors for them over there. In Ottawa, one of the biggest struggles they've had is actually the Ottawa Community Housing opted to use their own maintenance staff to do the panel build and install work, which makes perfect sense because they know the buildings the most. They're, their labor that's already on payroll. So, it's a cost control measures, it's logistically simpler, but the problem ended up being that the maintenance staff wasn't able to put in full-time effort into building and installing the panels. It sort of became the project that they did until, there was some, more important maintenance thing to take care of. So that really impacted their timeline. And they also ended up running into an issue where even though the strongest advice was to keep the brick facade in place, no, sorry, they did keep the brick facade. With them, it was the windows. They ended up wanting to remove the windows as they were going, as opposed to removing them after the install. And there was some clashing between the sort of team that's advising and recommending and and the maintenance staff, and it proved to be some difficulty there, but nothing they haven't been able to overcome. And they've managed to deliver the first pilot. Yeah, like I think it maybe has a couple of pieces of siding left to go, but yeah, they've managed to bring a rickety old, I think that building is from the 60s. They brought it up to net zero. It's one of the most efficient buildings in all of Ottawa right now. Next question is from Carlina. I'm gonna go with Carlina. Have any projects recovered individual houses? I was literally just having this conversation the other day with an engineer. So to lend a bit of insight, the way we're seeing this strategically happening in the coming decades, because it's not an immediate project, recover needs to start with as simple a building as possible, like the multi-unit residential building, like 6300. Because we need to keep the form factor simple, and we need to keep the list of problems to solve as short as possible. So our plan is to work on as many MURBs as possible, to develop a raft of solutions and a library of solutions that will allow us to be able to then start looking at single family homes and be like, okay, cool, we've got 70% of this figured out because of the work we've done over here. So now it's a much less daunting task, because single family homes have a couple of problems working against them. I appreciate that there is a lot of single family homes, and that is a problem that we're going to need to solve. But here's the linchpin. At the moment, where there isn't really robust incentives to make such substantial investments into retrofits, because it's not cheap. I mean, a retrofit isn't cheap. I mean, even a conventional one, a deep energy retrofit on an average house is still going to be $200,000, to get to like close to net zero or close to passive. It's a huge investment, and it's not incentivized yet. And where the system of panelization isn't made super efficient yet, there's a lot of lack of economy of scale that we're not able to take advantage of. And there still aren't enough incentives from various funding sources to make it happen. So it's an expensive proposition for a single family home, in part because of that surface area to volume ratio. It's a whole ass roof, it's 4 walls and whatever outcroppings and porches and things for just one family. Whereas a simple shoebox shaped MURB, it's those same, bigger, but the same 4 walls. The portion of walls and roof to one unit or one housing unit is much smaller. So the per unit cost is necessarily going to be lower with a MURB. All of that said, we aren't pursuing single family homes because of those reasons, but the aforementioned Peter Amarangan in Edmonton, I know that he's pursuing at least 1, possibly 3 single family home retrofits that are piggybacking on the work that they did for the Sundance Co-op, where they bring in a hollow panel bolted to the house, fill it with cellulose on site. That is being pursued by like enthusiastic early adopters, like clients who want to invest the money and want to make a statement with it. because it still isn't cheap to do, and it is an investment. It does give them a net zero home, which is great and absolutely the responsible thing to do, but money talks. So for the time being, the single family home for us is a longer term objective, because right now there's lower hanging fruit that can still yield really substantial results. For example, there's a housing co-op in Ontario. I don't remember how much of this is semi-confidential, so I'll have to be a little bit cagey about it. There is a housing co-op in Ontario that we're working with to help them retrofit, like, 10 unit, like 10 unit, not duplexes, once they're all townhouses, that's it, 10 unit townhouses, where, for one project, we've benefited and upgraded the lives of 10 occupants or 10 housing units, as opposed to, a similar amount of effort in terms of like research and problem solving and engineering going into a single family home, which only benefits one family. Not that that family doesn't deserve it, but, same amount of, it's the sort of cost to benefit, effort to benefit analysis. But that's the idea behind us moving ahead with pursuing these townhouses and these MURBs and these bigger projects that benefit more people at once, so that all those solutions, all that engineering that we put into that, we can start using that library to start solving the rest of the housing portfolio across the country. No more questions in the pile. Hopefully those answers were somewhat satisfactory. I hope everybody's enjoyed their time so far.
Yeah, that's awesome, Nick. Thanks. If anyone has any more questions, obviously you can pop them in the chat. But yeah, super engaging. And I was actually talking with a colleague earlier in the week, and we were talking about panelization and how it's kind of a game changer, because, like, if I'm not mistaken, like, in the construction industry, like, a lot of people get laid off in the wintertime because they're not on construction sites. But with manufacturing panels in actual facilities, I guess companies wouldn't necessarily need to be laying people off during the wintertime, and kind of changes the game a little bit.
Well, it does. It actually changes the game, not only in the sort of seasonal balance and control of it, but it also moves the needle substantially on dealing with the looming labor crisis. We are hemorrhaging carpenters to retirement, and the young pups are just not filling in the void. So we're gonna have a skilled trades, significant crisis before the end of the decade. And if we can cultivate these systems that are producing, meaningful amount of output for a much less burdensome amount of labor input, we can still remain, like, collectively productive without needing to have nearly as many people on the tools. Yeah, Brenda threw in some, those aren't questions. I thought those were questions. Brenda, glad you found it interesting. And like, coming from a construction background, I'm also super enthusiastic about this technology, because it allows us to be able to do a lot more per person hour. Because one of the things that was really frustrating me about, and brought me to my sort of existentialist crisis in the construction world, is, here we are, a team of 3, 4, 5, the crew size fluctuated. We're putting in collectively 10,000 hours a year to make all these projects happen. And really, it results in 2 houses a year, like 2 families benefiting from a year's worth of our effort. I'm like, cool, super happy to be helping those families. But if we were to put the same amount of effort into something like this, like that 10,000 hours of fabrication and panel install, that could be 2 apartment buildings that house 50 people. It's logarithmically higher potential for improving the lives of our fellow citizens. And it was just like, okay, this custom building is just, that's not flying anymore. So the scalability is a huge part of what's exciting about this for me. And like, from the very beginning, I saw as much as it's complicated to figure out how to retrofit a building with prefabricated panels, I'm not pretending it's simple. And yes, I understand there was a complicated slide about why conventional retrofits don't work. But the complication for the panelized retrofits is short-lived, because every time you solve a complication, you put it into the library and you can draw from it next time. Like ultimately what I'm pushing for, and with any luck, we'll be able to commit some meaningful research time into, is called the design toolkit. So picture with me, if you will. I probably should have put this in the slideshow, but some gestures and facial expressions will get it across. So let's say Claire, our host here, has decided that, cool, she's got a property in, I don't know, southern Saskatchewan. And it desperately wants to be net zero, heck, needs to be net zero because of all the crushing incentives to do so. That's the hope anyways. So what Claire has to do is take a sufficient scan. At the moment, the technology is LiDAR, but there's lots of emergent technologies. So she needs to get us that point cloud or that CAD drawing or whatever we deem to be sufficient input. And she just uploads that to the Recover interface, whatever that looks like. And then we've dialed it in that, okay, so now we know the panel layout that we need, because the algorithm goes like, okay, cool, I know the restrictions for what panel can fit where and how they intersect with this, that, and the other. I understand those details. We know that Claire's building in southern Saskatchewan, okay, it's in this climate zone, oh, it's this archetype, so 99 times out of 100, it's gonna have this kind of wall assembly, which means, boom, you need panel type F36. So we reach into the bucket of the panel F36 details and archetypes, feed that into the algorithm that is laying out and detailing those panels. We press the print button, and then that platform ends up spitting out, hey, cool, here's your installation and fabrication instructions, which can be sent back to Claire or some central fabrication facility for production. And the instructions are output in such a way that, you know, Claire's carpenter can set up or maybe Claire's strapping on the tool belt herself. I mean, why not? Trades are open to everyone. Whoever is fabricating has the instructions. Like, if you follow these instructions, the panels that you build will end up fitting on this building. That's the Recover guarantee. I don't know if we can guarantee that yet. We're a ways away from that. But the idea is, you know, scan the building, upload the building. A week later, or a satisfyingly short period of time later, you have the instructions ready to build, with the backing of the monumental amount of research that we've done to ensure that this panel installed this way on this building in this climate zone, you're going to be fine. We've assessed the condensation risks, we've assessed the structural integrity concerns, you're good to go. So instead of needing to do these incredibly exhaustive feed studies, like, you know, they're nearly $100,000 to do a feed study on whether or not it makes sense to do this to a building. It's like, okay, who's going to be investing that to pursue this kind of work? So taking all of those feed studies and everything that we've learned and turning it into a platform that can, I mean, I guess spit out, but quickly generate these reliable, proven, easy to build solutions, man, I can't wait to see that happen.
Ditto. Awesome, you've thought of everything. Or
yeah, thinking of it is one thing. Actually doing it, give me need a little bit more time.
Okay, we can give you that. But yeah, thanks, Nick, so much for coming out and giving that presentation. Super engaging. I think everybody enjoyed it. I know a couple of folks joined a little last minute. We are recording the webinar, so that'll be up. I'll send out an email, I think, with the link to the recording, so you all have access to it. And yeah, I think that concludes this month's Better Building Speaker installment. So thank you all for coming, and I'm gonna stop the recording, and yeah, everybody have a great night.
Good night all. Thanks for joining.